So in this particular video, we have a system of hanging block here. So here we have 3 blocks, 4 kilogram, 2 kilograms, and 1 kilogram. The 1 kilogram is hanging in the air there, and it says that the system here is frictionless. It wants us to find the tension in each cable. So I identified that there's one cable here connecting the 4 kilogram to the 2 kilogram, and then there's one more cable connecting the 2 kilogram to the hanging block of 1 kilogram. So in this particular problem, it wants us to find the tension in each cable and the acceleration in the block. So I will go ahead and show you how to do this. So the first thing you should do is identify the forces that it exists in the problem. Okay, so the first vector I like to draw out is the weight of the hanging block, because we know that exists. That is what's going to cause the system to accelerate. So here, the vector pointing downward, and by definition that is just the force due to gravity, and the force due to gravity is just mass times acceleration due to gravity. Okay, and what masses it is always the mass of the hanging block, and then opposing that would be the tension in the cable. So here I drew the green arrow for the tension in the cable, which I call T1, just slightly smaller. It has to be a little smaller in order for the system to accelerate downward. And then for the 2 kilogram block that is in the middle here, this vector is also T1. So T1 opposes the 1 kilogram, but it actually causes the 2 kilogram to move to the right as the system accelerates to the right. All right, and then the other cable that I have not accounted for is the one between the 4 kilogram and the 2 kilogram. So I will go ahead and put these two vectors up. They are equal in magnitude but opposite in direction, and both those red arrows is called T2. So I just went from right to left. You can go from left to right if you want. It doesn't really matter in the subscript. So the cable here is T1 in my work, and the cable here is T2. Okay, so let's knock this out. I encourage you, anytime you get these systems of hanging blocks, that you should try to draw a diagram just so that all the blocks is in the horizontal direction. Okay, and we take the line of motion to be positive. So in this case, the systems that I have here in the presentation moves to the right. So here's the 4 kilogram block in that order, the 2 kilogram block, and then the hanging mass, which is 1 kilogram. I just moved it up so that everything is horizontal. And then I would just translate this f of g pointing to the right. So if you open up the system, the f of g, while it is pointing downward, it can be drawn pointing rightward, because the system is going to move to the right. And what causes it to move is the force of gravity. So in this case, using common sense, I would draw f of g pointing to the right, because it's going to cause the system to move rightward. From there, you can transfer all your tensions in this horizontal diagram, which I think makes things a little easier to do and understand. Here's T1, here's T1, and then T2. I just have redrawn the arrows there. That's T2, and there's also T2. So each of the tension is drawn for you, and it behaves differently whether you use negative tension or positive tension, depending on the box that you're assessing. Okay? Let's do it. I've chosen to find the acceleration of the system first, because that's the easiest to do. To find the acceleration of the system, I need the net force of the system divided by the total mass, which gives me acceleration. So sigma F system equals m total times A. And then to find net force, the only force causing the system to accelerate is this force due to gravity of the hanging block, which I've drawn here pointing to the right. So if you're looking at the whole entire system, okay, this is an important visual. If you look at the whole entire system, the T's will always cancel out because they're opposite but equal in magnitude. So T1 pointing right, T1 pointing left always cancels out. It's almost like they don't exist if you look at the whole entire system. Okay. Likewise with T2, you have a T2 pointing right, but you have a T2 pointing left. So if you combine them, the net force is 0. So really, when it comes to net force of the system, look at the diagram and ask yourself, what is causing the systems to move? In this case, it would just be f of g, and it says frictionless, so there's no opposing kinetic frictional force. All right, and then this is m total, but we know this is pretty light work. What is the weight? The weight is contributed just by the hanging block, which is 1 kilogram. So my mass here is 1 kilogram. G is 9.8. Okay, and then m total is 7 kilogram. And then the only value that I don't know is my acceleration. So 1 times 9.8 is 9.8, and then to solve for A, we divide both sides by 7. So therefore, if you do that correctly, you should get a value of 1.4 meters per second squared. So for these types of problem, we take the line of motion to be positive. So even though the 1 kilogram block is technically moving downward, we take the line of motion to be positive. So the answer would just be 1.4 meters per second squared. Okay. So that's the answer for part for the acceleration, because it asks us to find the tension in each cable and the acceleration. All right, let's go ahead and knock out the tension here. So in no particular order, as you practice, you just have to figure out which one is easiest to do first. It didn't specify which tension it wants us to find. It actually wants each of them. So I always just do the easiest one first. I'll find T2 first because T2 to me is the easiest one to find. If I look at the 4 kilogram block here, the only force that's causing it to move is the tension T2 that's pointing to the right. So as the system is moving rightward, if you ask yourself, what is pulling this 4 kilogram block to the right? It is the cable in red here. So T2 is this vector. Okay, there's no opposing force here. So there's only one force that's causing the 4 kilogram to move. Therefore, to me, that's the easiest to do. So I'm going to set up net force here. For the 4 kilogram is equal to mass times acceleration, but I know that the net force for the 4 kilogram block is simply just one vector, and that is T2. So instead of writing net force, I would just call it T2 because it is the only one that exists for the 4 kilogram block. What mass here? Well, I have box here 4 kilograms, so if you're paying attention, the mass would be 4 kilogram. Okay, then we know mass is 4 kilogram because that's what we're assessing. The acceleration we already found in my work here on the bottom left of the screen, which is 1.4 meters per second square. If you multiply that, you should get 5.6 Newton. All right, the other way to do it, if you like, is using mass percent. Mass percent here is pretty straightforward. This strategy allows you to find the net force of the box. Okay, net force, not contact force necessarily, just to find the net force, and then what you do with that net force value is entirely up to you. Here, I put 4 over 7. The reason it's 4 over 7 is because this block here is 4 kilograms, and the mass of the whole entire thing is 7. 4 plus 2 is 6, 6 plus 1 is 7. And then I'm going to times it by the net force acting on the system. Well, the net force in this case is just F of G. And once again, the only force causing the system to move is the weight of the 1 kilogram block. This one right here. Okay. So therefore, my net force is simply F of G. But what F of G? F of G of the hanging block. So in this case, it would just be 1 kilogram times 9.8, which is 9.8 newtons. And if you do this on your calculator, you should also get a value of 5.6. Okay. Once again, even though I wrote out here net force of the 4 kilogram block, you have to recognize that for the 4 kilogram block, the only horizontal force that causes it to move is T2. So you can simply replace net force here with T2 because net force is the total, but the total in this case is only one vector. And what is that vector? T2. So really you can find T2 also doing percentages. As you can see, it's 5.6 Newton, which is the same values we got setting up Newton's second law going through acceleration. Okay, this does not go through acceleration. This uses acceleration. So find a strategy that you're comfortable with or practice both of them. All right, let's go ahead and find T1. Now that we're done with T2, the only other T we haven't found is T1. For T1, you have options, okay? You have the 2 kilogram block or the 1 kilogram block. I'm just gonna go ahead and use the 2 kilogram block perspective for now. To do the 2 kilogram block perspective, if you kind of box this stuff up like I have on my screen here, well, what's causing the 2 kilogram block to move is T1. Well, but as you pull it, there is this 4 kilogram block that's kind of like, you know, trailing behind it, slowing down. So there's T2 acting against it, okay? So to set up the Newton's second law for the 2 kilogram block in the center here, I have here net force is equal to MA, net force for the 2 kilogram block. Therefore, if I set it up, T1 minus T2, which is equal to MA, T1's bigger, T2 is less. Therefore, to solve for T1, I can just move T2 to the right side of the equal sign. It's negative here, move it to the right, it becomes positive. And then here we have everything already. We have M, which is 2 kilogram, because this is the perspective I'm doing. And then A is 1.4. And T2, we already calculated it up here. And T2 is just 5.6. If you add all those stuff up, you should get 8.4 newtons, okay? So that is using the perspective of the middle block. Now, if you don't like using the perspective of the middle block, your other choice and only choice that's left over is 1 kilogram block. because T1 also touches the 1 kilogram block. But if you use the 1 kilogram block, you have to, again, make sure you set up the physics correctly. So let's do it. The net force for the 1 kilogram block, I highlight this in yellow because you need to differentiate which perspective you're using. The net force for the 1 kilogram block is mass times acceleration. But I have two vectors here. F of g is going to be greater because we already established that it's going to cause the system to move. T1, well, T1 represents these two blocks that's kind of, slowing you down. They're trailing masses, so the only thing that they do is resist your motion. So therefore T1 is acting against you. So I'm just going to have F of g minus T1 is equal to ma. But if I need to solve for T1, I want to move negative T1 to the right side, which makes it positive, and I want to move this ma to the left side, which makes it negative. So if you do that in one step, you get F of g minus ma is equal to T1. Therefore, we know values already. What mass do we plug in for mg here? We plug in the mass of the hanging block, which is 1 kilogram, times gravity due to the surface of the Earth, which is 9.8. And again, all the negative signs for g has already been accounted for in this type of setup, okay? So when you get to these steps, g should be just 9.8 because the negative signs have already been taken care of. And then mass here, once again, is 1 kilogram because that's the perspective we're doing now. The acceleration is 1.4 meters per second square. And if you simplify that, you should get the same value of 8.4. So as you can see, there are options in terms of finding tensions in the cable. Pick a perspective you like, be consistent with your work, and make sure you plug in the right mass, and you should be okay. All right, I hope that helps. Stay nerdy, don't be whack.